So today we are going to start with the moving charge and the magnetic fields. New topic is consists of magnetic field. First of all, what is magnetic field? So magnetic field, see, it's the region near a magnet where a magnetic needle experiences a torque and it rests in a definite direction. So as we all know, magnet, suppose we have a strip of magnet. Magnet has few properties. First is the directive property that it always rests in a north-south direction. When we tie a magnet and suspend it freely with a thread, so magnet will lie in a north-south direction. Like poles of the magnet, they always repel each other, and unlike poles of magnet, they always attract each other. There are two poles of magnet, north pole and south pole. The north pole is the north pole of the magnet, is that pole of magnet which points towards the north of the geographic north of the Earth. And the south pole of the magnet points toward the geographic south of the Earth. Geographic north is actually the magnetic south of the Earth. And the geographic south is actually magnetic north of the Earth. So because opposite poles attract each other, that is why north pole of the magnet always lies toward the geographically north, which is actually the magnetic south of the Earth, towards that direction. And its magnetic south pole, the south pole of the magnet always lies towards the geographic south of the Earth, which actually is its magnetic north pole. And the space around a magnet where any needle or any magnet experiences a torque and it rests in that direction, definite direction, that is called the magnetic field. Then we'll start with the Oersted's experiment. So Oersted arranged a circuit and he experimentally found that suppose let me draw the circuit, please. Just hold on. Just a minute, please. Just a minute. Okay. Is the screen visible, ma'am?
Yes, visible.
Yeah. So Oersted, while explaining the current carrying conductor, so let AB is the current carrying conducting wire, which is connected to the pole of a battery through key, as we can see in figure A, first figure, you can say, right? And the wire is kept above a magnetic needle parallel to it in the north-south direction. You can see the needle over here, right? In a north-south direction, as it is placed over here. So long there is no current in the wire, so the magnetic needle will remain parallel to the wire. And as soon as we press the key, this key is pressed, a current flows through the wire and the needle is deflected. here we can see the deflection in the needle. In the second figure, the current started flowing from positive to the negative terminal. I mean, here it is flowing in the anti-clockwise direction, we can say. So north-south direction when needle is there, right? The current, and if we reverse the direction in this way, like we have changed the battery, now positive to negative current flows, so here it is flowing in the clockwise direction. The needle is deflected in the opposite direction. So the deflection of this needle indicates that with the passage of current in the wire, a magnetic field is established around it. And when we increase the current in the wire, or when we bring the needle closer to the wire, the deflection of the needle increases. So this experiment shows us that the magnetic needle, or the magnetic field is produced due to the effect of the current. So electric current is nothing but charge in motion. So it is concluded here that the moving charge always produces the magnetic field in the surrounding space. And if we bring another moving charge close to the into the magnetic field so produced, the field will exert a force on the moving charge or on the current carrying conductor. Right? Now we are going to see that what is the magnetic field due to the current carrying conductor, which was given by Biot-Savart law. We'll study in the Biot-Savart law. Right? So Biot-Savart law. So Oersted experiment showed us that a current carrying conductor produces a magnetic field around it. And there were two scientists, Biot and Savart from France, French scientists. They performed a series of experiments to study the magnetic fields produced by various current carrying conductors. And they formulated a law to determine the magnitude and direction of the field so produced. This law is called the Biot-Savart law. So let's say we have a XY conductor. So XY is the conductor here, right? XY conductor of say any shape through which current I is flowing. And here is a point P in air or in vacuum at which we want to find the electric field. So point P we have taken on the both sides, right? Here. So let us divide this conductor into infinitely small current elements of length say DL. And let IDL. IDL means we have considered this element DL and I is the current passing through it. So this is IDL, current element. Current element, right? Now, and let R be the position vector. So R is the, say, position vector, or we may say it's the distance. Let's say R is the distance of point P from the current element, from the current element, right? So according to Biot-Savart law, the magnetic field dB at point P due to the current element say IDL, right, depends upon following factors. So first is it is directly proportional to the current through the conductor. dB is directly proportional. Let's say, let me insert the symbol. This. dB is directly proportional to the current, right? So we can say directly dB is directly proportional to the current I flowing conductor, right? Second is it's directly proportional to the length dl of the conductor, right? Or dl of the current element, say element, right? So that is dB is proportional dB is proportional to the dl right? Then it is also, see, here we have theta angle. So dB is proportional to the sine of this theta. So it is proportional to the sine of the angle theta phi, say theta, right, between the current element and the line joining the element to the point, say P. So that is, we have dB is proportional to sine theta, right? Then fourth one is it's inversely proportional to the, it's inversely proportional to the square of the distance r. Square of the distance, say r, between the element and the point. And the point, right? So this is equal to, we have dB is inversely proportional to, sorry, 1 by r square. Right? Now, Combining all these factors we have, combining all these factors, we have dB is proportional to I, that is current element, then dl, that's the length element, then sine theta, right, whole upon r square. So on removing this proportionality, we have to remove this proportionality by some constant. So, and this relation is called the Biot-Savart law. This relation is called Biot-Savart law. Right? Now, we have dB equals constant, proportionality constant will be mu naught. This is mu, say naught by 4 pi, by 4 pi into, so we have IDL, let's say IDL sine theta, right? Upon r square. Right. So where mu naught जो है, that is the proportion, mu naught by 4 pi is the proportionality constant, right? So this is the expression for the Biot-Savart law, right? So because sine theta is involved here, and the direction of magnetic field is perpendicular to the plane of the current and the plane of this r, which is the distance, and the dl, current length element, current element. So Biot-Savart law in the vector form can be written as, so in the vector form, it is written as dB. So I'm writing it in bold, which indicates that it's vector dB, right, equals, so right. So here I can change this sine phi, right? I write over here I into, say, dl, that's a length element, into r vector. So these two will be written as bold. Fine. Here R3 will become R power 3. Right? So magnetic field at P due to entire conductor can be found by integrating this relation. Magnetic field due to say produced at P due to the entire conductor is given by Just a minute. By integrating, so we have B. So this is dB, sorry, equals dB equals just a minute, please. Integration where dB this is equal to, we have over here, so this is mu naught, right, by 4 pi, then again integration we have dl into r, this is vector r upon r cube. This is r, this is 3. That's the equation, right? So this is the equation. So where this mu naught by 4 pi right? Mu naught by 4 pi is the proportionality constant. Right? And mu naught is the permeability of free space. Free space. And the value of mu naught is the value of mu naught is equal to 4 pi into 10 to the power minus 7. 10 to the power minus 7. Right? 10 to the power minus 7 Newton per ampere square. Newton per ampere square. That's it. Now, so Biot-Savart law depends upon 4 factors. The magnetic field produced in the at point, say this P, it depends due to this current element dl, depends upon the current flowing through it. So it's directly proportional to current, right? It's directly proportional to the length of this current element dl. First, we'll find the magnetic field of this current element dl. Then we'll integrate that to find the magnetic field of this whole conductor over the whole length. Then it is proportional to the sine of the angle between the current element and this point P sine theta, right? And then it is inversely proportional to the square of the distance between the point P and the current element. Right? And when we'll combine all these vectors, we'll get this magnetic field is proportional to IDL sine theta by R square. And this is called the Biot-Savart law. This is called Biot-Savart law. So dB is mu naught by 4 pi. Mu naught by 4 pi is the proportionality constant, right? And in the vector form, we can write it as dB is equal to, this is mu naught by 4 pi, mu naught by 4 pi, right? Into IDL cross DL cross R by R cube. So magnetic field produced at point P, this is the formula to find the magnetic field due to current element. Now we need to find the magnetic field of the whole conductor over the whole length of the conductor, which can be found by integrating this. So this is mu naught by 4 pi integrating all this. So this is the relation we'll be using in the numericals also to find this magnetic field. And now what are the rules to determine the direction of the developed magnetic field? So rule number 1, this is the right hand palm rule number, right hand palm rule number 1, right? What does it state? It states that if we stretch our right hand, like I have shown in the figure, right? If we stretch our right hand such that the thumb points in the direction of the current and the fingers towards the point P at which the direction of magnetic field is to be determined, then the perpendicular drawn from the palm in the upward direction we can see over here will give us the direction of the magnetic field. Second rule is right hand thumb rule. So right hand thumb rule says, right, this is used to know the direction of magnetic field due to straight current carrying conductor. Straight current carrying conductor. It says that if we hold the straight conductor in our right hand such that the thumb points in the direction of the current, as we can suppose this is the conductor, right, holding in our right hand, the thumb points in the direction of the current, then fingers curl in direction of the magnetic field. Then fingers they will curl in the direction of the magnetic field. And there is another rule, Maxwell's right hand screw rule. So it states that if we hold the screwdriver in the right hand and rotate it in such that the screw moves in the direction of the current in the conductor, then the direction of rotation of the thumb will be the direction of the magnetic line of force. Right? So here we can see that the current carrying conductor is in the plane of this page, and the point P is also in the plane of the page. When we'll apply this rule, the magnetic field at a point P will be vertically downwards. And on the other side of the conductor, the field will be vertically upwards. Right? Now we'll do the applications of the Biot-Savart law. Applications of the Biot-Savart law. So first we'll find the magnetic field due to straight current carrying conductor of the finite size. So let's say this CD is the straight conductor in which current I is flowing, and P is the point at which the magnetic field is required. So let's draw a perpendicular from P to CD, which meets CD at point Q. and let the length PQ be, say, R. So here we have say CD is the length of the conductor. PQ is the perpendicular distance of point P from the conductor, and let the distance be, say, R. And let's say angle EPQ, E, P, and Q, this one. This is, say, angle phi. And angle FPE is a small angle, so D phi. And angle EFP, say, is theta. So angle QEP, this QEP will also be theta, because we can say this F and E lie very close to each other, as DL being very small. So this angle is also theta. Fine. Now draw, say, EG perpendicular from E on FP. So let me just write all this for you. So let CD be a straight conductor carrying current I, right? And P be a point at which the magnetic field is required, right? So now let us draw perpendicular from point P, which meets the conductor at Q, right? So let PQ be R. Let PQ be R. So let us consider a small element EF of the conductor, and let angle EPQ be, say, phi, angle FPE be D phi, and angle QEP. So this is QEP. First we'll write EFP, angle EFP theta. EFP equals theta. This equals theta, right? And angle QEP is also theta. Also theta. Why? As length of current element delta L, so DL, So this element, dl, right, is very small. Now let EG be perpendicular from E on FP. Right? And let say DL be the length of the element and x be its distance from the point P. By Biot-Savart law, we have Biot Biot-Savart law, the magnitude of the magnetic field at P due to the current carrying element DL is given by, we have this relation over here, let's say, or let me write here the equation. Is given by so this is dB equals, we have mu naught by 4 pi this is mu naught by 4 pi here we have IDL sin theta. This is IDL sin, we have theta by x square. So this is say x square, right? Now, from this figure, we know DL sin theta. In this triangle EFG, if we find theta, so length of the DL sin theta, so sin theta कितना होगा? ये 90 degree है. EEG is perpendicular to this here. So angle FG is 90 degrees. So this is theta. So sin theta will be EG upon FE or EG upon DL. So we get, we write by it. So DL sin theta. This is DL sin theta is equal to, we have EG in this diagram, EG by FE is equal to sin theta. F is DL. So EG sin theta, right? So this gives me, this is equal to X d phi. right? So therefore, we have dB equals mu, this is not, upon 4 pi, we have ID phi by x. This is sorry, ID phi by x. Now, so this is x. So how this x can be found? In this triangle EQP, we have cos phi is equal to r by x. In triangle EQP, let me write in triangle EQP, we have cos phi, right? Cos phi is equal to, this is r by x. R by x, right? So from this, we have x equals to, this will give me x equals r cos phi, using this value in the above relationship. Fine. So we'll use the value of this here in this relation. Let's, in place of d phi, we will write here I cos phi d phi, right? Upon, this is r. Clear? X is r cos phi. Right? Now, the magnitude of this, the magnitude of the magnetic field dB, or magnetic field B, sorry, at point P into the whole conductor CD. This is given by, let me insert the equation. So this is B equals so here we have so this is say phi 2 other angle phi 2 from, here we are considering it. This is phi 1. phi1 is on the negative side and phi2 is on the positive side. So we'll take minus phi1 to plus phi2. So this is lower limit will be minus phi, wait. Minus phi1 to phi2. Fine. So here we have this is mu naught by 4 pi, mu naught by 4 pi then it is I by say R. This is I. This is R. Right? We have cos phi d phi. Right? So integration of this will be this will be equal to mu naught by 4 pi mu naught by say 4 pi, right? This is I by R. Right? Then we have the square bracket. Anyways. This is sine phi. From minus phi to sine phi, right? Here write minus phi 1. Sorry. So this is minus this is minus phi 1 and this is phi 2. Phi 2, right? This is the equation. And which will give me final result of this. That is equal to we have say again mu naught by 4 pi, right over mu, then it is not mu naught I this is 4 pi mu naught 4 pi, right? R, you know, 4 pi R, then we have this is sine phi 2 minus sine phi 2 minus sine minus phi 1, right? N phi 1. So this gives me final answer. So finally, we'll get the magnetic field equals to